algebra. Okay. Algebra. Any questions before we start? Homework problems or any of the material in the lectures that I'm happy to go over?
Yeah, Professor.
Go ahead.
On the homework for the start of the equivalence relations, I just wanted you to kind of go over the math language of the last sentence on page 9. Because when you say it in class, I understand it, but then when I have to read it myself, I'm getting a little confused.
Oh, okay. Yes. So it is true. Like most science have their own language, whether biology or physics or math or whatever. So we have as x, and a relation r on x is just a set of ordered pairs. So officially, it's a subset of the product of x with itself, which is just all ordered pairs, x1, x2, where x1 is in x and x2 is in x. So this is all ordered pairs, and but the relation is just some of the ordered pairs. And we write if the ordered pair x1, x2 is in the relation, then we say x1 and x2 are related, and we write in general. I mean, in specifics, there's different notation. This is the general notation. That just means x1 is related to x2. And R is what is called equivalence relation if it has the following three properties. First, reflexive. That means every element is related itself for all x, and x. And you can think of equality as a model for this. Every element is equal, every number is equal to itself. So this is the reflexive property. It's symmetric, which means that if x is related to y, then y is related to x. It's like if x equals y, then y equals x. And the third is it's transitive, which means if x is related to y and y is related to z, then x is related to z. So in terms of equality, this is just saying if x equals y and y equals z, then x equals z. So that is sort of what you're familiar with. And whenever you have an equivalence relation, we have what are called the equivalence classes. So the equivalence class, and if you want to make sure that there's no uncertainty what the relation is, you can call it the R equivalence class. The R equivalence class element x in the set is, so this is the notation the book is using, square brackets around x subscript r. It's all elements in the set x which are related to x. So all y in x such that x and y are related, they're in their relation. And sometimes this is written all y in x such that instead of using the squiggle, they use these three lines. This is just notation. It's nothing new. And these equivalence classes see if this is the set x, capital X, if you take an element x subset, which is the equivalence class of x, everything that's related to X, some subset of the whole set. And these different equivalence classes partition the set. So the equivalence classes of R partition the set X. That just means every element in X is in one equivalence class. And if you take two equivalence classes, they either have no elements in common or they're exactly the same. So you can look at the set of equivalence classes. Which is denoted XR, and it's sometimes called the quotient of X by the relation R. This is the set of the equivalence classes. And so you can actually have a function from the set X into this set of equivalence classes. You call it, this is the function. It's like this is F. We're calling it this, where every element X in the set capital X gets sent to its equivalence class. And this is what the textbook is calling the classifying map. So the simplest sort of non-trivial example is if you take X to be the integers, and we say that X is related to Y if X minus Y is even. So if you have the integers, you have the equivalence class, like the equivalence class of 0 is just all the evens, all the even number. The equivalence class 1 is all the odd numbers. And this function, this so-called classifying map from Z, this relation, just write it as 2, mod 2 or 2Z, is just X to what? It's sent to either the set of even numbers, if X is even, and the set of odd numbers, if X is odd. So this quotient, Z mod 2Z, is a set which contains two elements, the even numbers and the odd numbers. So, and this map sends an integer to either the set of even numbers or the set of odd numbers, depending on whether the number you're mapping is even odd. So that's what they mean by the classifying map. It's just this map that sends an element of the set X to equivalence class in the quotient of X by R. So this is all part of the language of mathematics, and we see it here in algebra, but if you study more advanced calculus or geometry, the same sort of thing occurs over and over and over again. I don't know if that's helpful, or if that, I mean, I can explain more if you have more questions. I'm very happy to.
That's good. Thank you very much.
Professor, I had a question. Yeah. Can you help me understand question number 14B?
14,
I think it's on
page 7?
Yeah.
Okay. Yeah, so, okay. So this is exercise 14 beta. So you start with this set, which they're writing as n sub k, which is just the set of the first k integers. And then we have an example over here. So for example, n sub 3 is just the set 1, 2, 2, 3. And so in general, for any set x, what is called the power set of x is the set which is written as 2 to the power x. But of course, this is just notation because this is not a number. This is the set of all subsets of x. So for example, if n3 is the set with 3 elements, 2 to the n3, all the subsets of this. So what are the subsets? Well, you have the empty set. You have all the one element sets. You have the 2 element sets 1, 2, 1, 3, and 2, 3. And you have the whole set. So the power set of 2 to the n3 is this set, and there are 8 subsets, right? 1, 2, 3, 4, 5, 6, 7, 8. So that's what 2 to the n3 is. And we want to, and you notice this set has 3 elements. This set has 8 elements, and 8 is 2 cubed. And what they want you to show is that, what we'll show is that 2 to the n sub k, this power set, has exactly 2 to the k, or contains exactly 2 to the k subsets of nk. Right? That's how many subsets there are. We want to construct, this is the problem, 1-to-1 correspondence from the set of subsets of 2 to the nk to this set of just the first 2 to the k integers. Okay, so let's start by looking at an example. Well, here's an example. Maybe I'll start with an even easier example. So this is always a general strategy, especially in more advanced mathematics. You have a problem you want to solve. You need to, and it's not obvious how to solve it. You look at some simple examples. So let's look at the very simplest example. We take k equal to 1. So nk is just this, consisting of the 1 and 2 to the n. So this is n sub 1. So 2 to n sub 1. How many subsets are there? There are 2 of them: the empty set and the set just consisting of 1. And here we're being asked just to set up a map, a 1-to-1 correspondence from 2 to the n1 into n sub 2 to the 1, that's n2. This is just the set numbers 1 and 2, 1, 2. Well, of course, in this case, it's sort of easy because we're setting up a function from this set with 2 elements to this set with two elements. Let me just call the function f. Well, you can do this in lots of different. I mean, you could say f of the empty set is 1, and f of the set containing 1 is 2, right? This is a set with 2 elements. This is a set with 2 elements, and a 1-to-1 correspondence simply maps every element to a different element over here, right? Any questions about this? This is like the simplest possible example. Let's look at the next case, next easiest example. Suppose we take k equal 2. So N2 is the set of just the integers 1 to 2. And the power set are all the subsets of this. You have the empty set, the set just containing 1, this just containing 2, and this 1, 2. And n sub 2 to the k is 2 in this case, n sub 2 squared, or n4, that's the set 1, 2, 2, 3, 4. And we want to construct a function let's say f from the subsets of 1, 2, that is this set, to the set n4. I mean, you can do that in lots of ways, but let's try and find an interesting way to do that. So an interesting way would be the following. So in arithmetic, it's known, one can show that every positive integer is unique, a sum of powers of 2. Like, I don't take an integer, I don't know, 29. How can you, well, what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, and so forth, right? So the largest power of 2 that I could use to break down 29 would be 16. So that's 16 plus 13. 13, the largest power of 2 that goes into 13 is 8. 8 plus 5. The largest power of 2, no bigger than 5, is 4 plus 1. So 29 is 2 to the 4th plus 2 cubed plus 2 squared, and 1 is 2, 0. Okay. Any questions about this? Is a use fact. Let's take another number. I don't know, 87. So spend a minute or two and write 87, the sum of distinct powers of 2. And tell me what you get. What's the largest power of 2, no bigger than 87?
Two to the 6.
Sorry, is what?
2 to the 6, 64.
Okay, 64. So this is 64 plus 23. And then what's the largest power of 2 you can use for 23?
16.
So 23 is 16 plus 7. And how do you write 7 as a sum of power?
4 plus 3.
4 plus 3 is 3, and it's 2 plus 1. 1. We have 87 is 2 to the 6th plus 2 to the 4th plus 2 squared plus 2 to the first power plus 2 to 0. And you can show that this is unique. This is the only way you can write 87 as a sum of different powers of 2, right? These numbers are all different. 64, 16, 4, 2, and 1. They're 5 different numbers. You have 5 different powers of 2 here, and there's no other way to write 87 as a sum of different powers of 2. So that's a fact from arithmetic that I can use here, and let me apply it in this example where we let k equal 2. So the power set of n2, I'm just writing it down again, was the empty set 1, 2, and 1, 2, and 2 and n to the 2 to the k, which was n4, the set 1, 2, 2, 3, 4. Now, oops. If I want to define a function f from 2 to the n2 into n4, one way to do it is for every subset, let me just write s, in 2 to the n2, let f of that set s be equal to the sum of 2 to the power s for every s in the set capital S. So what does that mean? So in the set, in this power set, I said I had 4 different subs. So for example, if S is just the set containing the number 1, f of s is 2 to the first power, which is 2. If s is just containing 2, f of s is 2 to the 2 power, which is 4. If s the set 1, 2, then f of s is this is not a bad idea, but it's not the idea that I want to use. It's not work so well. In this would be 2 to the first power plus 2 squared, which is 2 plus 4, which is 6, and s of the empty set. And if s were the empty set, f the empty set would be 2 to the, I would just write 0 as 1. So let me not do that. Let me, so this fact about powers of 2 is very important. And in fact, that's an exercise on the next page. So let me find maybe a better way or a simpler way to prove this. So maybe we should just think of this, doing this step by step. So for example, for 2 to the n2, which is this set consisting of the empty set 1, 2, and 1, 2, I can map that to the set 1, 2, 3, 4 just by saying, let's say this goes to 1, this goes to 2, this goes to 3, this goes to 4. Right? That's all I have to do. And how do I extend that to k equals 3? So again, I'm just when k equals 2, 2 to the n2 is empty set 1, 2, 2, 1, 2. And we sent this to 1, this to 2, this to 3, and 4. This is set and 4. This was my function. When you go a equal 3, so 2 to the n3, this is subsets of 1, 2, and 3. So what are they? First of all, you have all the subsets just of 1 and 2. The empty set 1, 2, and 1, 2. And then you have all the subsets that contain 3. So I just can add 3 to each of these. So I have the set containing 3, the set 1, 3, the set 2, 3, and the set 1, 2, 3. And n sub 2 to the k, that's n8. That's the set 1, 2, 3, 4, 5, 6, 7, 8. So I already had a map from these 4 sets. This goes to 1, this goes to 3, this goes to 4. And I can extend it by just saying, take a set that contains 3, whatever the set without 3 got sent to, send this new set to that number plus 4. So this goes to 5, this goes to 6, this goes to 7, this goes to 8. So this is what is called proof by mathematical induction. Suppose we have two to the nk. So this is all subsets of 1 to k. And there's some function f that sends this to the set 1, 2, up to 2 to the k. So suppose we have this for some k. And now, what about k plus 1? So 2 to the nk plus 1, that's equal to these subsets. So all subsets that don't contain k plus 1, union with all subsets that contain k plus 1. So these sets get mapped to n sub 2 to the k, that is the numbers from 1 up to 2 to the k. And what numbers are left? All the numbers from 2 to the k plus 1 up to 2 to the k plus 2 to the k, which is 2 to the k plus 1. So I send a set here to 2 to the k plus whatever number the set without the k plus 1 gets mapped to. So that is one completely rigorous way to do this, but really to understand what I said takes some time at home or somewhere in a quiet place to think about this kind of construction. That's the idea. So you know, in calculus, you get simple problems like find the derivative of x cubed, and you learn a couple of rules about how to differentiate, and you can solve the problem. But in algebra, it's completely different. It's not just a matter of learning a couple of techniques. You have to learn some technique, but many problems involve a new idea or many ideas, and what you have to learn is how to come up with the ideas that let you solve the problem. Any questions about this or anything else? So what we were discussing last week was on the integers, on the set Z of all integers, positive and negative. The relation of congruence modulo, and there's such a relation for every positive integer m. And the relation is written x congruent to y mod m if m divides x minus y. So this is an equivalence relation. With equivalence classes, exactly m equivalence classes, because for every integer that's right, n, if you divide by m, you get a quotient q and a remainder r, such that n is mq plus r, and the remainder is 0 and m minus 1. So n minus r is m times q. This is divisible by m, and n is congruent to r mod m. And again, r is between 0 and m minus 1. So the equivalence class of n is the same as the equivalence class of r, and there only are, and there are at most m different equivalence classes of r. And in fact, they're exactly r equivalence classes, because if you take two numbers between 0 and m minus 1, the difference is not divisible by m unless the numbers are the same. So the quotient d mod mz, this of m equivalence classes, and we call them in this case, when the relation is congruence, they're called congruence classes. And in algebra, number theory, computer science, cryptography, many different areas, this is extremely important. And we proved congruence, or congruences, satisfy nice laws for addition and multiplication. For example, if a and a prime, that a prime, b prime are integers, and a is congruent prime mod m, and b is congruent to b prime mod m, then you can add the congruences. A plus b is congruent to a prime plus b prime mod m. And you can multiply the congruences. A times b is congruent to a prime times b prime mod m. So for example, suppose we take, I don't know, m equal to 7. So minus 8 is congruent to 6 mod 7. Why is that? Because minus 8 minus 6 is minus 14, and 14 is divisible by 7. And 3 is congruent to 17 mod 7. Because 3 minus 17 is also minus 14. No, let me pick a slightly different number. So it doesn't work. Say 13. Yeah. 13 is congruent to minus 8 mod 7. Oh, let me pick something completely different. $12 is congruent to 5 mod 7. $12 is congruent to 5 mod 7 because 12 minus 5 is 7. So if I add 12 minus 8 is 4, 5 plus 6 is 11, and 4 is congruent 11 mod 7. Because 4 minus 11 is minus 7. If I multiply, you see 12 times 8 is minus 96. 5, 6 is 30. Is this correct? Is minus 6 congruent to 30 mod 7? So minus 96 minus 30 is minus 26. If I divide 7 into 126, goes exactly 18 times. So 7 does divide minus 126. So this is correct also, right? So this is just an example of the fact that one can add and subtract. Well, one can add and multiply congruences. Right? And if you look at set of congruence classes, that is the quotient, this also is something very interesting. So if A is congruent to A prime mod M, then the equivalence class of A equivalence class of A prime. And if B is congruent to B prime mod M, then the equivalence class of B is equal to the equivalence class of B prime. Suppose we want to define addition of congruence classes. So if we have the congruence class of A and the congruence class of B, this is a question mark, doesn't make sense to define this as congruence class of A plus B. So is this well defined? And what that means is if A and A prime are in the same congruence class and B prime are in the same congruence class, is it true that the congruence class of A prime plus the congruence class of B prime, which by this definition would be the congruence class of A prime plus B prime, is that equal to the congruence class of A plus B? And the answer is yes. That's what we just proved, that if A is congruent to A prime and B is congruent to B prime, and a plus b is congruent to a prime plus b prime. So what this says is that there is a well-defined way to add congruence classes. So Z mod MZ, this is the set of congruence classes of the integers mod M, has a well-defined addition. And similarly, a well-defined multiplication. So we can not only add integers, and we can not only add congruence classes, and sorry, we can not only add integers, and we can not only add congruence, but we can also add congruence classes. Someone in the chat asked, what kind of pencil is this? It's a mechanical pencil that they sell at Staples. And yeah, so if you go to Staples and you go look for mechanicals, which is together with like drawing sometimes, whatever. That's all it is. It's just the mechanical pencil of Staples. But it uses very thick leads that I like and good for the Zoom. All right. Any questions about this? Well, we're in the process of in this first year of the book, which does not have a lot of pages, but it does contain a lot of material, is we're just studying really arithmetic now, properties of the integers. And when you study algebra or number theory, or a lot of mathematics, you use to prove things the principle of mathematical induction. And that is equivalent to an even simpler statement, which is sometimes called the minimum principle. Which says that every non-empty subset of n, and remember, is the positive integers, has a smallest element, contains the smallest element. So if you have any set of positive integers that's not empty, then it contains an element which is the smallest element in the set. And you might say, well, that's sort of obvious, but it's important to keep in mind that this is not true for sets of positive real numbers, that is, or even sets of positive fractions. So for example, if you take the set 1, a half, a third, a fourth, a fifth, a sixth, and so on forever, this set contains no smallest element, because for every 1 over n in the set S, if 1 over n is in S, then n plus 1 is also in S, is smaller. So for sets of positive real numbers, and even just sets of fractions, there is no smallest limit. But for a set of integers, there is. right? So every non-empty set of positive integers always contains the smallest element. And a corollary of the maximum principle is what is called the principle of mathematical induction, which says that if S is a subset of the integers with the following two properties, a subset of the integers such that first of all, 1 belongs at S, and 2 is in S, then n plus 1 is in S. So S is subset integers. It's not empty because it only contains 1. And whenever it contains a number n, it contains the successor, the next number, n plus 1. So F is such a subset, then in fact, S is the set of all positive integers. And the reason why the principle of mathematical induction follows from the minimum principle, you could say, let's see, well, here's the minimum principle. So proof that the minimum principle implies the principle of mathematical. Namely, so we have a set at S with 1 in the S, and the property that n in S implies n plus 1 is in S. If S is not the set of all positive integers, then the complement, I'll call it T, every positive integer that's not in S is not empty. So if S is not the set of all positive integers, oh, excuse me 1 second. So S is a set that contains 1. 1 has the property that whenever n is in S, then n plus 1 is in S. And this is a proof by conjugation. If S is not the set of all positive integers, then the complement of n and n, call that set T. This is every integer in n that's not in S. That's going to be non-empty. Therefore, by the minimum principle, T contains a smallest element. I'll call it n naught, because every non-empty set of positive integers contains the smallest n naught, an element, n naught. But n naught can't be equal to 1 because 1 was in set F. So therefore, n naught has to be at least 2. Because if it's a positive integer and not 1, it has to be at least 2. And n naught is the smallest integer in T. So n naught, smallest element of T, means that a smaller number, n naught minus 1, is not in T. And n naught minus 1 is a positive integer because n naught is at least 2. Which means n naught minus 1 is in S. But for every number in S, its successor, you take n naught minus 1 plus 1, that's n naught. That is in S. And this is a contradiction, because you cannot have n naught in S and n naught in T. So therefore, S has to be all the integers. Right? So this is a proof that the minimum principle implies the principle of mathematical induction. And there are many very, very important principles, laws, identities that we prove using mathematical induction. So here's an example of examples using mathematical induction. So the first couple certainly come up in calculus when you're learning integration. You have the following formula. If you take the sum of the first n integers, that's equal to n times n plus 1 over 2. For all n greater than or equal to 1. Okay. Of course, you can check that this is true. When n equals 1, on the left-hand side, you get 1. On the right-hand side, you get 1 times 2 over 2, which is 1. When n equals 2, on the left, you have n plus 2, which is 3. On the right, you have 2 times 3 over 2, which is also 3. N equals 3. On the left, you have 1 plus 2 plus 3. On the right, you have 3 times 4 over 2, and they're both equal to 6. When n equals 4, on the left, 1 plus 2 plus 3 plus 4. On the right, 4 times 5 over 2, and you can check, they're both equal to 10. So this statement is true for n equal 1. And then we just checked it's true for n equal 2, 3, and 4. So assume the statement is true for some number n, and I want to prove it n plus 1. That means I want to look at I'm looking at the set of all n for which this is true. True is true for 1. I want to show that if n is in the set, then n plus 1 is in the set. So to say that it's true for n means 1 plus 2 plus 3 up to n is equal to n plus 1 over 2. So the question is, what happens when we add up all the numbers up to n plus 1? 1 up to n plus 1. The sum of the first numbers is n times n plus 1 over 2, and then we're adding n plus 1. And now we just do some elementary arithmetic. If I factor n plus 1 out of this, I get n plus 1 times n over 2 plus 1. N plus 1, n over 2 plus 1 is n plus 2, 2. And that's exactly this formula with n replaced by n plus 1. When you replace n by n plus 1, you get n plus 1 and n plus 2 over 2. So that's a proof by mathematical induction. Right. Again, you might not have proven this, but you certainly should have seen this in Math 176 and Calc 2, because you use this in proving some of the beginning formulas for integration. You also prove the next result, or use the next result in calculus, where instead of adding up the integers from 1 up to n, for I going from 1 up to n, you're adding up the squares. Yes, 1 squared plus 2 squared plus 3 squared plus 4 squared up to n squared. And this is equal to n times n plus 1 times 2n plus 1 over 6. That's what we want to prove. So let's just check small cases. Of course, the most important is n equal. When n equal to 1, you just have 1 squared, which is 1 on the left. On the right, when n is 1, 1 times 2 times 3 over 6, also equal to 1. So that's good. When n is equal to 2 on the left, that's 1 squared plus 2 squared. That's 1 plus 4, which is 5. On the right, when n is 2, you have 2 times 3 times 5 over 6. This is 30 over 6. This is also 5. So it checks. When n equals 3, 1 squared plus 2 squared plus 3 squared is 1 plus 4 plus 9, which is 14. On the right, when n is 3, this is 3 times 4 times 7 over 6. 3 times 4 is 12. 6 into 12 is 2. 2 times 7 is 14. So it also checks. So how do we prove this by mathematical induction? A statement is true for n. You have to prove it for n plus 1. So what does it mean to prove it for n plus 1? You have to add up the squares of the first n plus 1 integers. 1 squared plus 2, 3 squared, up to n squared plus n plus 1 squared. Let's see, what does that equal to? Of course, by the induction hypothesis, the sum of the first n squares is equal to this. So this is n plus 1 over 2, 2n plus 1 over 6, plus n plus 1 squared.
Can you scroll down a little bit, Professor?
What do we do next? Well, I have no idea, but you have to do something. So I don't know, what can you do? Well, I could put this over a common denominator of 6. And then I see I have an n1 here, n plus squared over here. So I can factor out an n plus 1. So this is the 1/6. I can factor out the 1/6. So I have n plus, well, I'll do it in 2 steps. N times n plus 1 times 2n plus 6 n plus 1 squared. Factor out an n plus 1, I have one of these and one of these. I have n plus 1 over 6, n times 2n plus 1 plus 6 times n plus 1. I just factor out an n plus 1. Let me just expand this. This is n plus 1 over 6. This is 2n squared plus n plus 6n. That's plus 7n plus 6. And if I remember my high school algebra, I can try to factor this. I have n plus 1. I can factor this I think, into n plus 2 times 2n plus 3. This is 2 squared plus 7n plus 6. That's exactly right. And 2n plus 3, I'm running out of space. I can write 2n plus 3 as 2 times n plus 1 plus 1, because this is 2n plus 2 plus 1. And that's exactly in my original formula. I'm trying to prove this for n plus 1. If I replace n by n plus 1, I get n plus 1, n plus 2, 2 times n plus 1 plus 1. That's exactly what I have here. So it checks. So that's a proof of this result by mathematical induction. Questions about this? Okay. There's also what is called the binomial theorem, which tells us how to expand x plus y to the n. And the expansion involves some numbers called the binomial coefficients. So you remember that for k greater than or equal to 1, k factorial is the product 1 times 2 times 3 up to k. It's the product of the first k integers. And we also define 0 factorial to be 1. So the binomial coefficient. So for k between 0 and n, binomial coefficient is written as n over k in parentheses, and it's read n choose k. This is defined to be n factorial divided by k factorial times n minus k factorial. So if you haven't worked with or even seen these numbers before, they're very important. For example, let's just do some examples. 4 choose 2, I'll make it 5 choose 2. This is 5 factorial over 2 factorial, 5 minus 2 factorial. 5 factorial, 2 factorial, 5 minus 2 is 3, so that's 3 factorial. This is 1 times 3 times 4 times 5 over 1 times 2 times 1, 2 times 3, 3. I can multiply out and divide, or I can just say, well, I can cancel 1 times 2 times cancels this 1 times 3. 2 into 4 is 2. 2 get 2 times 5. So this binomial coefficient 5 choose 2 is equal to 10. Right. What is 7 choose 3? That's going to be 7 factorial over 3 factorial. 7 minus 3 is 4 times 4 factorial. So that's 1 times 2 times 3 times 4 times 5 times 6 times 7 over 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. Again, the 4 factorial cancels that. 2 times 3 is 6, cancels the 6. So I just get 5 times 7, or that's 35. And it's an interesting observation. It's always true that even this looks like a complicated fraction, the denominator always divides into the numerator. So this is a positive whole number. So for example, just so you have some of the fun, why don't you calculate 10 7. figure out what that binomial coefficient is. And tell me what number you get. What could it be? Exactly 120, because this is 10 factorial over 7 factorial times 3 factorial. So 10 factorial, just multiply all the numbers up to 7, 8, 9, 10. 7 factorial is all the numbers up to 7. 3 factorial is 1 times 2 times 3. These cancel. This is, let's see, 3 into 9 goes 3. 2 into 8 goes 4. 4 times 3 is 12. 12 times 10 is 120. So that's the binomial coefficient. And the binomial theorem tells us how to expand x plus y to a power. So x plus y to the first power is x plus y. X plus y squared is x squared plus 2xy plus y squared. X plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. X plus y to the fourth is x to the fourth. Well, I mean, you can multiply this out, but I know how to do it. But it's just multiplying, right? It's nothing fancy here. This is, you're expanding these, you just multiply, and you get some polynomial x and y. And if you look at the maybe what's x plus y to the 0? That's just 1. And if you look at the coefficients that you get, here it's just 1. The coefficient of x is 1, the coefficient of y is 1. Here the coefficients of the terms are 1, 2, 1. Here the coefficients are 1, 3, 3, 1. Here the coefficients are 1, 4, 6, 4, 1. And so on. This is actually a famous triangle, and this goes on forever, of course, because you take x plus y to the 5th, you get x to the 5th and 5x to the 4th y, and maybe 10x cubed y squared, 10x squared y cubed, 5xy to the 4th, y to the 5th. So these coefficients are 1, 5, 10, 5, and 1. You get this triangular array of these coefficients. This is called Pascal's triangle. And they have very pretty properties. You down the edges, it's always a 1. But everywhere you look in each number is the sum of the two numbers above it to the left and the right. Like 3 is 1 plus 2. 4 is 1 plus 3. 6 is 3 plus 3. 10 is 1 plus 5 is 1 plus 4. 10 is 4 plus 6, and so on. This is, if you haven't seen Pascal's triangle before, it's very pretty, and people have studied this a lot for hundreds of years. And it's also the case, if you check, that these coefficients are actually exactly the binomial coefficients. So 5 is the binomial coefficient, 5 choose 1. 10 is the binomial coefficient, 5 choose 2. 10 is also the binomial coefficient, 5 choose 3. 5 is also the binomial coefficient, choose 4. 1 is the binomial coefficient, 5 choose 0. And that's the case with all of these examples. And this is a special case of the phenomenon, the theorem, which says that for every positive integer or every non-negative integer, even n, x plus y to the n, it's a sum. When you expand this, when you multiply it out, you get a sum, k going from 0 up to n. The highest power of x is x to the n. The highest power of y is y to the n. You get things of the form x to the k, y to the n minus k for all k from 0 to n with some coefficient. And the coefficient is always the binomial coefficient. So that's the binomial theorem. I want to prove this by mathematical induction. Now, let me just make one quick remark. So remember the definition of the binomial coefficient, n choose k, is n factorial over k factorial n minus k factorial. And I said this is true for k between 0 and n. So when k is equal to 0, what do you get? You get n factorial, 0 factorial, n minus 0 factorial. 0 factorial is 1. So this is n factorial over 1. N minus 0 is n over n factorial. That's equal to 1. And n choose n is n factorial over n factorial minus n factorial. That's n factorial over n factorial times 1. That's also 1. And maybe to prove the binomial theorem by mathematical induction, we have the following. Suppose I take n plus 1, choose k. I claim that this is the same as n choose k plus n choose k minus 1 for all k between 1 and n. So you might need an identity, something like this to binomial theorem, but let's just check this identity. N choose k plus n choose k minus 1. What is n choose k? The definition factorial, k factorial, and minus k factorial. And what is n k minus 1? It's n factorial over k minus 1 factorial and minus k minus 1 factorial. This is n factorial over k factorial n minus k factorial plus n factorial over k minus 1 factorial, and this is n minus k plus 1 factorial. So I'm adding fractions. Let me try and put them over a common denominator. K factorial is the product of the integers from 1 to k. So that's k minus 1 factorial times k. So I see I want to get, if I multiply top and bottom by k here, I get k times n factorial over factorial n minus k plus 1 factorial. and here, if I want the same denominator, I have to multiply the numerator and denominator by n minus plus 1. It's n minus k plus 1 times n factorial. And when I multiply the denominator by n minus plus 1 factorial, I get k factorial n minus k plus 1 factorial. And now these two fractions have the same denominator, k factorial. I'll write this as n plus 1 minus k factorial. And in the numerator, I have this plus this. And if I factor out an n factorial, I have n minus k plus 1 plus k. And the k's cancel. So this is n factorial times n plus 1 over k factorial n plus 1 minus k factorial. And n factorial times n plus n plus 1 factorial over k factorial n plus minus k factorial. And that's exactly n plus 1 choose k. So I proved this identity. So let me jot that down again. So n plus 1 choose k is equal to n choose k plus n choose k minus 1 for k between 1 and n. And what I want to prove is that x plus y to the n is summation. K goes from 0 to n choose k, x to the k, y to the n minus k. So assume this is true for n, and we want to prove it for n plus 1. So what is x plus y to the n plus 1? It's 1. That's the same as x plus y times x plus y to the. That's x plus y function hypothesis times this. Summation k goes from 0 up to n choose a x to the k, y to the n minus k. If I just distribute this is x times this sum plus y times that sum. So x times this sum is summation. K goes from 0 to n choose k, x to the k plus 1, y to the n minus k, plus summation k goes from 0 to n choose k, x to the k, y to the n plus 1 minus k. So now I have to use some clever high school algebra. Let me just write this as summation k goes from 0 up to n choose x to the k plus 1. I'm going to write n minus k is n 1 minus a plus 1. Of course, those cancel. And plus summation k, and k goes 0 up to n choose k, x to the k, y to the n minus k. Here, if I replace k plus 1 with k, this is the same. See, as k goes from 0 to n, k plus 1 goes from 1 to n plus 1. So I'm going to replace k by k minus 1. This is n, choose k minus 1, x to the k, y to the n plus 1 minus k, plus the sum k goes from 0 up to n choose k, x to the k, y to the n plus 1 minus k. So here, let's see the term, right. When k, just write the sum from k equals 1 to n choose minus 1 and x to the k, y to the n plus 1 minus k. And I also need the k equals n plus 1. And when k is n plus 1, this is n choose n, x to the n plus 1, and y to 0. And here, some k go on up to n choose k, x to the k, y to the n plus 1 minus k, together with the term when k equals 0, which is just y to the n plus 1. So this is x to the n plus 1 plus summation, k goes from 1 up to n. I'm just putting these two together. I have n choose k minus 1 plus n choose k, x to the k, y to the n plus 1 minus k, plus y to the n plus 1. And this we just proved is n plus 1 choose k. So this is x to the n plus 1 plus summation, k goes from n plus 1 choose k, x to the k, y to the n plus 1 minus k, plus y to the n plus 1. And this, lo and behold, is exactly what we wanted to prove. So, some of you are probably in math ed and going to end as, let's say high school math teachers, and this is really high school algebra, but at a very advanced level, right? There's a lot of technical skill and manipulation involved in doing this, and that's what it is. All right. Any questions about this? In the text, these are all left as homework problems, but they're difficult homework problems, which is why I wasn't planning to assign them as homework, at least, but I wanted to go over them here. Okay. All right, we are done for the morning. Chilly outside, so stay warm, be well. I have office hours this week, I think, Monday, Wednesday, and Thursday at 1:30 on the same Zoom login. So if you have questions, you are encouraged to log in. Ask whatever you would like. Anything before we go? Okay. Then we are done for the morning. See you on Wednesday. And happy Valentine's Day, everyone.
Thank you. You too. Bye.
Bye.
Thank you. You too.
Have a nice day.
Bye.
Thank you.